is wrong with this pointer. Okay, laminar flow. The flow is characterized by smooth, streamlined, and highly ordered motion. So that too is actually the two characteristic of the laminar flow. While of course, opposite of laminar flow is turbulent flow, and the characteristic of the turbulent flow is that we have a velocity fluctuation, meaning that we have sometimes the fluid is slow and sometimes the fluid is moving much faster, and the second one is highly disordered motion, where we have a lot of disturbance here lah, right? And the transition from laminar to turbulent flow does not occur suddenly. Okay, at the right side, okay, this figure here, it shows a simple example between laminar and turbulent flow. I think this is, you can see during your secondary, during you take you learn chemia or something in chemistry, where you light the Bunsen, Bunsen, okay. So you can adjust the airflow into the pununu, and you can differentiate, okay, where we have the flame there, either it is in laminar or turbulent flow. Yeah, okay, turbulent flow. Okay, the third dimensionless number in that is important in convection is Reynolds number. Because in Reynolds number, okay, the transition for laminar to turbulent flow depends on the surface geometry, surface roughness, flow velocity, surface temperature, and type of fluid. I think it is similar to the factors that influence the convection. Okay, the flow regime depends mainly on the ratio of the inertial forces to viscous forces in the fluid. The ratio is called the Reynolds number, which is expressed for external flow as Reynolds number equal to inertial forces divided by viscous forces, which is VLC divided by V small v equal to rho VLC divided by mu. Okay. At large Reynolds number, of course it is focused on turbulent flow. The inertial forces are large relative to the viscous forces. Okay, as you can see, for large Reynolds number, inertial forces large compared to the viscous forces, while the small or moderate Reynolds number, which is for laminar flow, the viscous forces are large enough to suppress this fluctuation and to keep the fluid in line. That's why we have a smooth streamline, right? So there is no fluctuation of the velocity, and of course no highly disordered distortion. Okay, the typical Reynolds number, the Reynolds number at which the flow become turbulence. Okay, so we look into the, I think this is first or second subtopic, which is the forced convection, parallel flow over flat plates. Again, if you can't really understand what is explained or displayed in the slides, you can also refer to the small books. Okay, the transition from laminar to turbulent flow depends on the surface geometry, surface roughness, upstream velocity, surface temperature, and the type of fluids. The transition is best characterized by the Reynolds number. So again, this figure it shows again the difference of laminar and turbulent flow. Okay. So if we have a flow of fluids, a movement of fluids, flow over a flat plate, we have a plate here. So at the beginning we have the flow is in laminar flow, and after some point the fluid flow become turbulence. Okay, force, okay, the film temperature. So of course, this is one of the parameters that we need to find if we want to solve a calculation problem regarding on convection. Okay, the first one we need to find is film temperature, where we just TF equal to T surface temperature plus environment or surrounding temperature divided by 2. Okay, after that we can calculate the Reynolds number by using the this formula below, which is Rex equal to rho Vx divided by mu, or Vx divided by small v, where we want to calculate at where the Reynolds number at the distance x from the leading edge of the plate. Okay, in engineering analysis, a general accepted value for the critical number is Ra critical equal to rho Vx critical divided by mu, which is 5 times 10 power of 5. Okay, the actual value of the engineering critical Reynolds number for a flat plate may vary from 10 to the power of 5 to 3 times 10 to the power of 6, depending on the surface roughness, the turbulent levels, and the variation of pressure along the surface. Yeah, I mean, this is the usual value that being used when we want to calculate. Okay. Okay, the average friction coefficient over the entire plate is determined by, okay, for coefficient for of friction for laminar flow. Okay, this is the formula. I mean, as you can see that the Reynolds number for laminar is less than 5 times 10 to the power of 5. But for turbulence, okay, it range in between power 5 power of 5 times 10 to the power of 5 and 10 to the power of 7. Okay, or if you want, so from this value, yeah, you need to substitute into this formula to find the friction coefficient, okay, for the entire plate. Okay, depending on the type of flow given in the question. Okay, this is okay as I think we have discussed in the earlier slide. Okay, for Nusselt number also we need as we have two type of flow for convection. Of course, the Nusselt number, I mean, will be different for laminar flow and turbulent flow. Okay, so this is formula Nusselt number, how we want to find or determine the Nusselt number for laminar flow, and the bottom one will be the formula for Nusselt number in turbulent flow. Again, as you can see that the Reynolds number, okay, will be different. Okay, if we have Reynolds number which is less than 5 times 10 to the power of 5, and the Prandtl number is larger than 0.6, so we need to use the Nusselt number for laminar. And for the turbulent, okay, if we have we calculate the Prandtl number which is in between of 0.6 until 660, and of course the Reynolds number is larger than 5 times 10 to the power of 5. Okay, we are going to use the formula, the Nusselt number formula for turbulent flow. Okay. When a flat plate is subjected to uniform heat flux instead of uniform temperature, the Nusselt number is given by, okay, so this is another formula for Nusselt number. For this one is Nusselt number for laminar. The bottom one will be okay, for turbulence. Okay, right. I mean, this is for Prandtl, the Reynolds number is still the same lah. Okay, we have the same consideration. So this one you need to really to understand, okay, which one is for lamina, which one is for turbulent flow. Okay, for the formula for, I mean, Nusselt number, Prandtl number, and Reynolds number, it will be given as appendix in your test lah, during your test or in your final exam. The only thing is that you need to choose the correct formula. Okay, I think that's all for the first part of convection, where we have discussed fourth convection, parallel flow over the flat plate. Okay, I mean, even though this slide is not fully discussed how to use all the formula, I mean, you can usually we should discuss how to use the formula during the tutorial session, right? But I think we just need to wait for me to prepare the video clip uh, video clip for discussion of on the tutorial part. Okay, so thank you.